Before I start talking about integrating power series, anyone has any questions? Hello, anyone has any questions? Okay, good evening, good evening. So last class, I was not able to finish 6.1. So we're going to finish 6.1, then go to two very important series, Taylor series and the Maclaurin series. But let's talk about the integrating power series first. So just like differentiating power series, we can represent a function as an infinite power series, and then when we differentiate the function, we can differentiate the power series term by term. Can you extend the due date for homework 17? Okay, I will do that. 17, did I assign 17? Oh, yes. 17. Okay, no problem. 17, let's do it now. Let's see. Right, next week, we finally have a little break. So let's see, 19 plus 7. Let's do both 26, okay? So including today's homework. All right. Any other questions? Okay, let's see these two examples. So integrating power series. For each of the following function f, find a power series representation for f by integrating the power series for f prime and find its interval of convergence. So A is f of x equals to ln of 1 plus x. And B, f of x equals the arctangent of x. So for ln of 1 plus x, the derivative is 1 over 1 plus x, right? That is what we know before. And 1 over 1 plus x can be represented as 1 over 1 minus negative x, geometric series, right? Then we see the ratio, the first term is 1 in the geometric series, and the ratio is negative x. And that can be represented as a power series of negative x raised by n from 0, for n from 0 to infinity. Because again, we want the first term to be 1. So the first term to be 1, we want n start with 0. Anything raised by 0, that's 1. If we write out a couple of terms, we will get 1 minus x plus x squared minus x cubed, so on and so forth. But this one, to be able to represent in power series, we have to have a condition. The condition is the absolute value of the ratio, in this case, absolute value of negative x is the same as the absolute value of x less than 1. Right? Then to find the power series for ln of 1 plus x, we can integrate, right? We can integrate the power series term by term. That's the beauty of it. So now integrate f prime of x. So it's the same as integrate the power series. So we can integrate it term by term. When we integrate, this is an indefinite integral, so we add a constant c to it. Integration of 1, that's x, negative x, integration negative x squared over 2. Integration of x squared, that's x cubed divided by 3, so on and so forth. So we get a representation for f of x, or ln of 1 plus x. right? ln of 1 plus x is the integration of 1 over 1 plus x, right? So this is the power series, and of course we can write in summation signs, right? Writing summation signs as alternating series because the term is from positive to negative, positive to negative. So we write it as -1 raised by n plus 1 because n start with 1 now. So we want n start with 1 for this case. So -1, the first term we want to be positive. So we have -1. It doesn't have to be positive. Oh, it has to be positive, right? Because 1 plus x has to be greater than 0. There's a domain of ln, log function. So 1 plus x has to be greater than 1. That means x has to be greater than 0, which means x is positive. So the first one is positive, so we do -1 raised by n plus 1, because the first term will be 1 plus 1, -1 raised by square. So index is sometimes is tricky, so we have to pay attention to the index, how to index it right. Then we see the term, we have x raised by n over n, right? That's the nth term, because the first term will be x raised by 1 over 1. The second term will be -1 raised by 2 plus 1 over 3 will be -1. Then x raised by 2 divided by 2. So this is to use, to integrate a power series. So this is one of the example. Anyone has any questions? Okay, let's keep moving. We cannot forget about the condition, okay? Without this condition, it's not true. The condition is the absolute value of the ratio has to be less than 1 for geometric series to converge. Oh, we need to find the interval of convergence. I didn't talk about the constant c. But for constant c, we have, because ln of 1 plus 0 equals 0, right? Because ln 1 is equal to 0. So we have c equals to 0, right? Because constant term means that x, all the x is 0, right? Then we just substitute 0 into ln of 1 plus x. So get 0. That's why the constant term is just 0. So to find the interval of convergence, we have the ratio, absolute value of the ratio is less than 1. So it's from -1 to 1, not including -1 to 1. But however, what happens at x equals -1 and 1? If x equals -1, we go back here, we see we have -1. So at x equals -1, the series becomes a harmonic series, or harmonic series diverges, right? So we see, okay, so we keep open parentheses for -1. At x equals 1, at x equals 1, we can substitute this in. At x equals 1, we get an alternating harmonic series, right? We get an alternating harmonic series. So we know alternating harmonic series converges. So the interval of convergence is from -1 to 1, but not including -1, however, includes 1. So we need to check the boundary points. Anyone has any questions for this? Okay, now example B, the function is arctangent x. arctangent x, we know the derivative of arctangent x is 1 over 1 plus x squared. Right? So if we integrate its derivative, so we get back to arctangent x. So what do? We still write as geometric series. So 1 over 1 plus x squared, we write as 1 over 1 minus negative x squared. So the ratio is negative x squared. And of course, we have to have the condition. Absolute value of negative x squared has to be less than 1. And when we simplify that, we get absolute value of x less than 1. So now to find a power series for arctangent, we just integrate 1 over 1 plus x squared. And we can integrate term by term. So from this geometric series, we can write some terms. Okay, so we get 1. So that as negative x squared raised by n. Because the first term a is 1, so now we want to index with 0. Because n equals 0, anything raised by 0 is 1. So we write out a couple of terms. We get 1 minus x squared plus x raised by 4 minus x raised by 6, so on and so forth. We see, so this is alternating series. To integrate, we just integrate term by term. Indefinite integral, so we start with c, a constant term. Integration of 1 is x, integration of negative x squared is negative x cubed divided by 3, so on and so forth. Then we can write as, then we can find out c, right? What is c? C is when x equals to 0. So arctangent of 0 equals to 0. So which means the tangent 0 equals 0. So c equals 0 in this case as well. So arctangent x has a representation of x minus x cubed divided by 3 plus x raised by 5 divided by 5, so on and so forth. And we write in the summation sign. We write it as a negative 1 raised by n, alternating series. The first term is positive, so we start index with 0. And then x raised by 2n plus 1, because we see x raised by 1, next term is x raised by 3, then next term is x raised by 5, right? The increase is by 2. So we have 2n x raised by 2n plus 1. The denominator is the same as the exponent, so divided by 2n plus 1. Of course, we have to have this condition for the ratio, for the absolute value of x less than 1. Then, so the interval of convergence is from negative 1 to 1 with open parentheses and closed parentheses. Now we check boundary points. We check at x equals 1 and x equals negative 1. Then we find out x equals 1, the series converges. Negative 1 also converges. So the interval of convergence is from negative 1 to 1, including negative 1 and 1. Okay, anyone has any questions? What is the relevance of c equals 0 again? Oh, so when we integrate, right, when we integrate indefinite integrals, we get a family of functions, right? So we have to include in the c. Because when we differentiate, constant differentiating any number that's 0. So when we integrate 0, we get a constant, we get a number, c. So we have to find out this c. So what do? We just substitute into the function, right? Because why do we want to do 0? Why do we plug in 0 for x? Because when x is 0, all those terms become 0. So that's how we find out c. So we plug in 0 for x, right? Like here, arctangent of 0, that equals 0. So that means c equals 0. Does that make sense? not making the, oh, okay, not making the equation to be 0. So we always plug in x to be 0. So plug in x equals 0 to find the c value. Because you see the function is this, right? So arctangent of x equals to c plus x minus x cubed divided by 3, so on and so forth. Look at the chat, I'm typing in the chat. So when we plug in 0 to get c plus all zeros, you see that? Which means in this case arctangent, okay. So c is just the function plug in 0 for it. It's like calculate one question about displacement, find VT and ST. Exactly, yeah, integration. The integration process is the same. Okay. All right, let's try this one. So checkpoint 6.9, integrate the power series ln of 1 plus x equals to, so this is given. So what do? We write out a couple of terms, term by term, to evaluate integration ln 1 plus x dx. Okay, let's all try this. Write maybe like a 3, 5, 4 or 5 terms to see the pattern. Actually, if you don't want, it's right here. X minus x squared divided by 2. Right. That's ln of 1 plus x. Just read 1, 2, 3, 4, 4 terms. And the 4 terms is enough to see the pattern. Then integrate this. Okay. Okay, so when you finish, you may type your answer into the chat. So we have what format is the answer? Is it just x raised by n minus 1? Negative 1 raised by n, x raised by n over n minus 1 times n, x raised by n times n minus 1. Yes, right, very close. Just right, you won't be able to write down the summation sign. So let's go to the whiteboard to do this. So let's write out, so ln of 1 plus x. We can write out a couple of terms. It's x minus x squared divided by 2 plus x cubed divided by 3 minus x raised by 4 divided by 4, right? So on and so forth. We want to integrate this. We want to integrate this. So when we integrate, what do we get? First we get a constant term, then plus x squared divided by 2 minus x cubed divided by 2 times 3, right? Because we had a negative x squared divided by 2. When we integrate, we get negative x cubed divided by 2 times 3 in the denominator. Then plus x raised by 4 divided by 3 was there before in the denominator, now multiply by 4. Then minus x raised by 5 divided by 4 was there before, now 4 times 5, right? So this we see a pattern. We see a pattern. Let me use the pen. We see a pattern. So we read out. Well, let's find the C first, right? So plug. So ln integration of. Hold on a sec. Right. So again, ln integration of ln, we still get 0, right? Let me tap first, then add the sign. So ln 1 plus 0. So what's the value of this? So that's a C term, right? That's a C. Because when x is 0, all the x terms are gone. All the x terms become 0. So we plug in x equals 0, get a C. Well, ln of 1 plus 0 is ln 1, well, which is 0, right? So integrate 0. It's a C. You know what? Yeah, this is annoying C. So this one, because we won't be able to tell, because the integration of C is just a constant, it's a number. Let's ignore this for now. Let's focus on those guys. So let's try to find a pattern of this. Okay, so we see we have alternating ones. So what do we want to do? So first we want to do -1, or raised by a number. So this number is to do with this index variable n. Because our first term is positive, right? Our first term is positive, and also, so let's write x also. So x start with 2. So if we want n, so we can let n start with 1. So if n start with 1, we see x is n plus 1, right? The first term, because the first term is 2. 1 plus 1 is 2. Then the first term is positive. So -1, we also want to do n plus 1, because the first term will be 1 plus 1 squared will be positive. Then we have to figure out denominator. Denominator, we see the first one, the denominator is 1 times 2, right? Seems like n times n plus 1. The second term is 2 times 3. The other term is 3 times 4. So we have this, right? So integration of this, we can represent with this. Anyone has any questions? All right, let's keep going. Okay, let's see this theorem. So uniqueness of power series. So let's see, we have Cn x minus a raised by n and Dn times x minus a raised by n be two converging power series such that, and those two equal to each other for all x in an open interval containing a. Then Cn has to equal to Dn for all positive, for all non-negative n's. So this is saying power series is unique. Okay, a convergent power series is unique. Okay, so that's the part I didn't finish. I was not able to finish last class. So today we're going to two important power series, Taylor's series and Maclaurin's series. So they're so important, so they get a name. So we're going to describe the procedure for finding a Taylor polynomial of a given order from a function. And we'll see what that means, given order, okay? And explain the meaning and the significance of Taylor's theorem with remainder. And we'll estimate the remainder for Taylor series approximation of a given function. Okay, overview of Taylor/Maclaurin series. Consider function f that has a power series representation at x equals to a. Remember, a is the center of the power series. Then the series has the form of Cn multiplied by x minus a raised by n. Right? A is the center of convergence. What should the coefficient be? So what are those C0, C1, C2 can be? So if at the center, of course, if x equals to a, so the series is just C0. So the series equals to f of a, right? If the coefficient C0 equals to f of a. So C0 is easy to find. So we would like the first derivative of the power series to equal to f prime of a at x equals to a. So we see that if we differentiate the power series, so we will get, differentiate C0, we'll get 0, right? So C0 disappears in the derivative. So we get C1, we get C1, right? That's just f prime of a, right? So C1 equals to f prime of a. Right? So C1 f prime of a, you know, so on and so forth, right? So if we differentiate the second order of differentiation, so we would get a 2C2, right? 2C2, because here we have 2C2. When we do double differentiation, we get 2C2. And we know that's f double prime of a. So on and so forth. We would get a 3 times 2, C3. Right? So double prime, f of double prime of a is 2C2, f triple prime. So we see this pattern, right? So C2 equals f double prime of a divided by 2. And C3 equals f triple prime of a divided by 2 times 3. So on and so forth, right? So that means the coefficient of Cn can be represented as a derivative, right? Can be represented as derivative. So basically, the f raised by n of a divided by n factorial. You see, the constant term C0 is just f of a, and C1 just f prime of a times x minus a, f double prime, C2 equals f double prime of a divided by 2 factorial. So on and so forth. Damon, what do you mean slash? Anyone has any questions? Oh, don't worry about it. Don't worry about it. So this is a key part, right? So this is a key part of this, from a power series going to Taylor's series or Maclaurin series. Let's go back a little bit. So normally, right, a power series represented as this. So Cn times x minus a raised by n. And this Cn can be represented with derivatives of the function at a. So instead of writing Cn, we're writing as this. We're writing Cn as this. F, you know, the nth nth degree of derivatives, right? N can be 1, first order derivative, n equal to 2, second derivative, so on and so forth. So the Cn, the coefficient, can be represented as derivative of a at nth order divided by n factorial. Okay, so then the series of Cn times x minus a raised by n can be represented by this, right? F of a plus f prime of a times x minus a, f double prime of a divided by factorial, 2 factorial, x minus a squared, right? We have a constant term, we have a linear term, we have a quadratic term, so on and so forth. All right, now with this, we can define Taylor series. If f has derivatives of all orders at x equals to 8, if the derivative does not exist at x equals to 8, we won't be able to talk about f nth order of derivative, right? So we have to have this condition. Then the Taylor series for the function f at a is such. All right, is this. So normal C1, C0, C1, C2s. All those C's are represented with a function f of a or derivative of f of derivative or second derivative divided by 2 factorial, third derivative by 3 factorials, nth derivative divided by nth factorial, and evaluated at 8. Okay, so the Taylor series for f at 0 is known as Maclaurin series for f. All right, so Taylor series is in general, right, centered at 8. Maclaurin series is a special case. It's for the function centered at 0. So as you can see, when a is 0, so Maclaurin series is just f of a plus f prime of a of times x, f double prime of a divided by 2 factorial of x squared, so on and so forth. So normal a in the formula, right? Just x. Anyone has any questions? Okay, so this is the definition, right? So it came from a power series of Cn times x minus a raised by n. Now, we use the derivatives to represent all the C's. And the centered at a, we call Taylor series. When a equals 0, centered at 0, we call Maclaurin series. And those two series are very useful. And the Taylor series is unique. If a function f has a power series at a that converges to f on some open interval containing a, then that power series is the Taylor series for f at a. Okay, so it's unique. Let's see this one. So this one, see the nth partial sum of the Taylor series for a function f at a is known as the nth Taylor polynomial. All right. So, for example, the zeros, the first, second, third partial sums, and we call just the order. Okay. So this is a constant, right? Constant is just first term. And so we call this first order of Taylor series. So because it's linear because this is raised by 1. So x minus a raised by 1. So the power for x is 1. So the exponent for x is 1. So it's a first order. First order is linear, right? So it's a linear representation, or we call first order of Taylor polynomial. And if when we take a quadratic form, x minus a squared, this is a quadratic we call second order of Taylor polynomial. Just like a partial sums, right? We just take the first couple of terms. We take the constant term and the linear one, we call first order. We take the constant term, the linear one, and the quadratic one, we call second order because it's x raised by square. The order means the leading term. So the leading term here is x raised by square. So we call second order of Taylor polynomial. Or if we include the third power, so we have we have a constant, we have linear, we have quadratic, we have third one. So the leading term is x cubed, right? Of course, with this f triple prime of a divided by 3 factorial, x raised by 3. So x raised by 3, 3 is the highest power. So we call this third order of Taylor polynomial. Okay, so these partial sums are known as zeros, first, second, and third Taylor polynomials of f at a. If a equals 0, then this polynomial is also known as Maclaurin polynomials for f. So we now provide a formal definition. So if f has n derivatives at x equals a, then the nth Taylor polynomial for f at a is this. So P represents a polynomial, right? So Pn of x equals f of a plus f prime of a, x minus a, plus f double prime of a divided by 2 factorial, x minus a squared, f triple prime of a divided by 3 factorial, x minus a cubed, plus until nth order. So this is called nth order Taylor polynomial. The nth order Taylor polynomial for f at 0 is called nth Maclaurin polynomial for f. Right. So we now show how to use this definition to find several Taylor polynomial for f of x equals ln x at x equals to 1. Okay, let's see an example. Find the Taylor polynomials P0, P1, P2, and P3 for f of x equals ln x at x equals 1. Use, okay, we don't care about the graphing. We need to find f prime of x, f double prime of x, and f triple prime of x, right? So f of x equals ln x, f prime of x equals 1 over x, and f double prime of x equals negative 1 over x squared, f triple prime of x equals 2 over x cubed. Then x equals 1, so we evaluate at 1, f of 1 equals 0, f prime of 1 equals 1, f double prime of 1 equals negative 1, f triple prime of 1 equals 2. So we calculate the primes, okay? We calculate the primes up to the order. Then we evaluate at the given point, at the given a. Right, here we're given a as 1. So now we have all those values. We just plug in the definition of Taylor's polynomial. Right, P0 of x means just a constant term, f of 1, which in this case is just 0. P1 of x is the constant term plus the linear one. So f prime of 1, and x minus 1, which will simplify, we get x minus 1. We see a linear function, right? So first order is a linear function. 0 order is a constant. Yeah, so this is consistent with polynomial. Remember we used to call polynomial of degree 0, polynomial of degree 1, so on and so forth. Polynomial of degree 0 is constant. Polynomial of degree 1 is linear. Polynomial of degree 2 is quadratic. Okay, so same thing here. We call 0 order Taylor series, first order of 0 order Taylor polynomial, first order Taylor polynomial. Then when we include the quadratic form, right, we simplify, we get this. So we see this is second order Taylor polynomial. Then we including the third power, right? So we call third power Taylor polynomial. So we say f of 1, which is 0, f prime of 1 times x minus 1, f double prime of 1 divided by 2, f double prime of 1 is negative 1. So that's why we got negative half x minus 1 squared, because a is 1. Then f triple prime 1 divided by 3 factorial, f triple prime 1 is 1, or it's 2. So 2 divided by 3 factorial, that's 1/3. So x minus 1 cube. So we see we have linear, we have quadratic, we have third power. So the leading term is x cubed, 1/3 of x cubed. Anyone has any questions? Why is it over 2 and not 2 factorial? Oh, 2 factorial is exactly 2, because 2 factorial is just 2 times 1. Right? It should be 2 factorial, but 2 factorial is 2, so they just didn't bother to write 2 factorial. What was the purpose of evaluating the derivative if those values were not used? What was the purpose of evaluating the derivative if those values? Damon, it's used. It is used. You see here, you see first power, let's go back. You see f of 1 equals 0, right? F of 1 equals 0, f of 1 equals 0. So f of prime of 1 is 1, f prime of 1 is 1. So this one simplify, we just get x minus 1. And we plug in to the second one, f of 1 is 0, f prime of 1 is 1, so we just got a x minus 1, which is here. And then f double prime of 1 is negative 1, right? Negative 1, so get a minus half. You see all the derivatives being used. F of 1 is 0, f prime of 1 is 1, so we have 1 times x minus 1, so we have x minus 1. F double prime of 1 is negative 1, so we have negative half here. F triple prime of 1 is 2, so 2 divided by 3 factorial, that is 1/3. So you see we have 1/3 of x minus 1 cubed. Okay. All right. So, right, to find certain order of Taylor polynomials, we calculate derivatives. Then we plug in a. Then we put it into the formula. So this is a graph, right? This is saying, a graph, partial sum, the constant term, we get this. The linear function, we get a line. Quadratic function, we get this. And the cubic function, we get. So this is all different, all the graphs for those partial sums, for the degree 0, 0 order, first order, second order, or third order. Okay, let's all try this one. All right. Let's find derivatives maybe up to third power, right? So remember P naught just f of 1. P1 is f of 1 plus f prime of 1 times x minus 1, because a equals 1. P2 equals the f of 1 plus f prime of 1 times x minus 1 plus f double prime of 1 divided by 2 factorial x minus 1 squared. P3 is f of 1 plus f. Actually, we don't need to do this. P3 is just P2. P2 plus f triple prime of 1 divided by 3 factorial x minus 1 cube, right? P2 is just P1 plus f double prime of 1 divided by 2 factorial x minus 1 squared. So all I have to do is calculate the derivatives. Oh, okay, so Paul get already. So f of 1, just 1, right? So that's just P naught. So P1 equals 1 plus, what was the derivative? F prime of x equals to negative 2 over x cubed. So f prime of 1 equals negative 2. F double prime of x equals to negative become positive. So 6 over x raised by 4. F double prime of x equals to 6. F triple prime of x equals to negative 24 over x raised by 5. So f triple prime of 1 equals to negative 24. So we plug in f prime is negative 2, so we get a 1 minus 2 times x minus 1. We simplify, we get a linear function. So we get a 1 minus 2x plus 2, which is negative 2x plus 3. P2 is just P1 plus f double prime of 1, which is 6, divided by 2 factorial, then x minus 1 squared, which is 3. So P2 is negative 2x plus 3 plus 3 times x minus 1 squared. And P3 is P2 plus f triple prime of 1, which is negative 24, divided by 3 factorial, which is 6, x minus 1 raised by 3, so which is negative 4. So P3 is 1 minus 2 times x minus 1 minus 3 times x minus 1 squared, minus or plus? I get a plus 3 times x minus 1 squared minus 4 times x minus 1 cubed. Right? Okay, so you can keep going. So let me go to this. So f of x equals to 1 over x squared. So what do? We want to find out f prime of x f prime of x equals to negative 2 over x cubed. Then f double prime of x equals to negative 3 times negative 2, which is 6. 6 over x raised by 4. F triple prime of x equals negative 4 times 6, negative 24, divided by x raised by 5. Okay, because we have to do to up to third order, so we only calculated this. Now we want to evaluate at a equals to 1. So f of 1 equals to 1. F prime of 1 equals to -2. F double prime of 1 equals to 6. F triple prime of 1 equals to -24. Right. Then we plug into the formula. So the formula is P naught equals to f of 1, which is just 1. P1 equals to P naught plus f prime of 1 times x minus 1. We simplify to get a 1. F prime of -2 times x minus 1. P2 equals to P1 plus f double prime of 1 divided by 2 of 2 factorial multiplied by x minus 1 squared. We simplify, so P1 is equal to 1 minus 2 times x minus 1. And f double prime of 1 is, f double prime is 6. 6 divided by 2, which is 3. So plus 3 times x minus 1 squared. Then last one, we want to find a P3. P3 equals to P2 plus f triple prime of 1 divided by 3 factorial multiplied by x minus 1 raised by 3. P2 we already know, so 1 minus 2 times x minus 1 plus 3 times x minus 1 squared. Then now f triple prime of 1 is -24. -24 divided by 3 factorial, which is 6, which is -4. So minus 4 times x minus 1 raised by 3. Okay, so the 0-order Taylor polynomial is 1. First-order Taylor polynomial for this function is 1 minus 2 times x minus 1. Second-order Taylor polynomial for this function is 1 minus 2 times x minus 1 plus 3 times x minus 1 squared. And third-order Taylor polynomial for this function f is 1 minus 2 times x minus 1 plus 3 times x minus 1 squared minus 4 times x minus 1 cubed. Of course, we can keep going, right, to find a fourth order, fifth order, so on and so forth. Anyone has any questions? So again, it's just calculating the derivatives of the function and evaluate at the given a. Then plug into the Taylor polynomial definition. Okay, now let's keep going. Okay, Maclaurin polynomials, just, 0. So the a equals to 0. So let's see here. We want to find P0, P1, P2, P3. But for a, the function is e to the x, b sine x, c cosine x. All right, those are famous functions. We do the same thing. Well, for e to the x, all orders derivatives are the same. It's just e to the x. So we just evaluate at 0, right? Because the Maclaurin series is centered at 0, a equals 0. So f of 0 equals e to the 0 equals 1. For any other order of derivatives, is still e to the 0 equals 1. So all the order of derivatives is just equals 1. So now we just plug into the function, right? So P naught is just f of 0 equals 1. And P1 equals the P naught plus derivative, first order derivative multiplied by x. So just get a 1 plus x, linear function. P2, we get P1 plus second derivative at 0 divided by 2 factorial. Right? Second derivative is still 1. 1 divided by 2 factorial is half. So plus half x squared. P3 equals P2 plus f third power of derivatives, which is still 1 divided by 3 factorial with 6. So 1 over 6 x cubed. So we see the pattern. Actually, we don't need to evaluate the factorial because the factorial give us a pattern. So we see for third power, we have 1 plus x plus half x squared plus 1 over 3 factorial x cubed. Or we can write as 1 plus x divided by 1, x plus x squared divided by 2, plus x cubed divided by 3 factorial. And we see the pattern actually, right? We see the pattern nth power, nth order. We get 1 plus x squared divided by 2 factorial, plus x cubed divided by 3 factorial, plus x raised by n divided by n factorial. So this is the nth order Maclaurin series for e to the x. So if we want to write in the summation sign, we can write as x raised by k divided by k factorial. K start with 0 because the first term is 1. So first term is 1, so we want to index k starting from 0 up to n, right? Up to n. So this is nth order polynomial representation for e to the x, for the function e to the x. It's powerful, isn't it? So the function e to the x, exponential function, can be represented as a polynomial function. Is that mind-blowing? That's kind of mind-blowing, right? First, that's how important polynomial function is. And second, this is almost saying, for known functions, we can, not all the functions, but some very important functions can be represented as polynomials. Right? It's very powerful. It's very powerful. Okay, let's keep going. So that's e to the x. Now let's see sine x. So let's take the derivative of sine x. First derivative is cosine x, second derivative negative sine x, third derivative is negative cosine x, fourth derivative come back to sine x because it's a periodic function, right? Periodic function. So evaluate at 0 because we want to find its Maclaurin representation. So f of 0 equals 0, f prime of 0 equals 1, f double prime of 0 equals 0, f triple prime equals -1, first power derivative equals 0. So we see a lot of terms will diminish. And actually we see the pattern. If the even order derivative gets 0, odd order derivative we get -1 raised by a power. So we write in this, we write as So zero Maclaurin power, zero order Maclaurin series is just zero for sine x. And first order is 0 plus x, right? Just x. So second power, because it's 0, second order is 0, so still get x. So we see P1, P2 are the same. So first order Maclaurin polynomial and the second order are the same. Because all the zeros, right? The zeros kills a lot of terms. And third order, we get x minus x cubed divided by 3 factorial. Fourth order, we get the same as third order. Fifth order, we get x minus x cubed divided by 3 factorial plus x raised by 5 divided by 5 factorial. So we observe the pattern, so we get x minus x cubed divided by 3 factorial plus x raised by 5 divided by 5 factorial. So for the nth term, we get -1 raised by m, x raised by 2m plus 1 divided by 2m plus 1 factorial. So we can write as summation sign, -1 raised by k, x raised by 2k plus 1 divided by 2k plus 1 factorial. Right? So we remember a couple of terms, first couple of terms, x minus x cubed divided by 3 factorial, right? Alternates, the sign alternates. So the next one you can imagine will be minus x raised by 7 divided by 7 factorial. The next one will be plus x raised by 9 divided by 9 factorial, so on and so forth. So we have all those odd exponents for x. Any questions? Now let's see cosine. And we know cosine just 90 degree shifting of sine, right? Horizontal shifting of sine. So that means, well, let's see. So we can always graph all those. So for cosine, we do the same thing. We find the derivatives in each order. We evaluate at 0. So we also get a lot of zeros, so which means a lot of terms will diminish. And we get a P naught equals to 1, P1 equals to 1, P2 equals to 1 minus x squared divided by 2 factorial, P3 equals to 1 minus x squared divided by 2 factorial, P4 and P5 are the same, 1 minus x squared divided by 2 factorial plus x raised by 4 divided by 4 factorial. Right? Compare this one with sine. Sine, we have all the odd exponents for x. And cosine, we have all the even ones, even exponents for x. And of course, we can write it in summation sign. That would be -1 raised by k, x raised by 2k, divided by 2k factorial. If we graph of that, we get all those kinds of graphs. All right. Any questions? All right. Nice, huh? E to the x, sine x, cosine x can be represented as polynomial functions. It depends on the level. I shouldn't say can be represented, can be approximate as polynomial functions. When the order goes up, the approximation gets more and more accurate, as the graph shows, right? P naught is a straight line. P1, where is P1? Well, I don't see P1. P1 is the same. P0, P1 is the same. So P2 is this, right? P4 is this. So can you imagine if we do P1 million, right? It will get closer and closer to the real function cosine x. So what is the use, right? So you may ask, why do we want to use the Taylor series and the Maclaurin series? We use them to approximate. So when you punch into calculator for sine, let's see sine, maybe you plug in sine, let's see 20 degree. So if you plug into calculator sine 20 degree into your calculator, what does your calculator do? Your calculator does exactly Maclaurin series. Depends on how expensive the calculator is, the approximation will be different. You know, if you get a very, very expensive calculator, you know, it will calculate more terms. So it will calculate to up to a very higher order. So the approximation will be very, very close to the function. So that's why exactly, so when you punch into sine 30 degree, you get a half, you get a 0.5. But other than that, if you punch into sine 35 degree, the calculator just return you a approximate value, which behind the button of your calculator, it does exactly Maclaurin series. It's just approximate. All right, so that's the, okay, so now let's see this checkpoint. So find formulas for the Maclaurin polynomial up to third order for 1 over 1 plus x. And find a formula for the nth Maclaurin polynomial. All right, so let's all try this. So we calculate its derivative up to third order. Excuse me. And remember this one, we can also use a geometric series, right, to represent. We just take the first four terms. -1 raised by k, x raised by k start with 0, right? Right, 1 minus x plus x cubed plus x squared minus x cubed. Yeah, it's alternating series. 1 minus x plus x squared minus x cubed plus x raised by 4, so on and so forth. Yes. And also you can think about it's a geometric from the point of view of a geometric representation. But yes, so okay, so anyone like to see the calculation? Should we go over the calculation together? Okay, let's do that. Okay, let's do that. So the function is, let me just change this one a little bit. Let me see if I could. Right, so it's 1 plus 1 plus x by the denominator. Right, the denominator. And the Maclaurin series is just f of 0, right? And f prime just -1 over 1 plus x raised by 2, right? Then f prime of 0 is -1. Double prime, we have -2 times -1, it becomes +2 divided by 1 plus x raised by 3. Then we calculate f of 0, f double prime of 0, that's just 2. F triple prime, we have -3 times 2 get -6 divided by 1 plus x raised by 4, right? Then f of triple prime of 0 is equals to -6. Okay, now we just plug in, right? So P naught just equals to f of 0, which is 1. P1 equals P naught plus f prime of 0. Well, center at 0 now, so just x. No more x minus 8. F prime of 0 is -1. Right? So we get 1 minus x. And P2 equals P1 plus divided by 2, just x squared, no more x minus 1. Again, centered at 0. So get 1 minus x, or f double prime of 0 equals to 2. 2 divided by 2 factorial is just 1. Let's get x squared. So P3 equals P2 plus f triple prime of 0 divided by 3 factorial. Then just x cubed. We'll have 1 minus x equals 1 minus x plus x squared. Now, f triple prime of 0 equals -6. -6 divided by 3 factorial is -1. It's just minus x raised by 3. Anyone has any question? We can also see from the geometric series, right? In geometric series, we can write function, we can write f of x equals to 1 over 1 minus negative x, right? So the ratio is negative x. Then we see this one, we can write as n goes to 0 up to infinity. We only need the first couple of terms, right? Then negative x, because the first term we want to be 0, so that's why I want to start from 0, nth term. Right, second term we see we can write a couple of terms. So we see the couple of first terms are this, right? When n equals 0, we get a 1. When n equals 1, we get negative x. When n equals 2, we get x squared. When n equals 3, we get minus x cubed. Right? So Maclaurin series just take the first one. So Maclaurin's order, so 0 order Maclaurin series, just a function value. First order linear function in this case. Second order Maclaurin series quadratic function. Third order cubic function. So each one is a polynomial. So this is approximation. So that means we can use those polynomial functions to approximate this function. That's the beauty of this. That's why Maclaurin series and Taylor series are so important in mathematics, because the calculator does exactly this. The calculators, use this. Okay, anyone has any questions? All right, so now let's go back. Okay, Taylor's theorem with remainder, right? Remember Taylor series, Maclaurin series are power series, right? They're infinite. And so far, we only talk about order. We only go a couple of terms, right? So what do we do with the remainder? The remainder, there are infinite many terms. But we want to see when we approximate with a function, we want the remainder to go to 0. Okay, let's see. So remainder n, so we want to represent it as f of x, the function value, subtract the polynomial. Of course, because f of x, we want the f of x right in 2 parts. So the nth term, partial sums, or the nth order of Taylor polynomial, plus the remainder. So the remainder, we're going to use this, Rn of x. So nth order Taylor series, Taylor polynomial, Pn. Pn is nth order Taylor polynomial. So Rn is the rest of the terms in the infinite series. All right, so Taylor series is an infinite series. So when we represent a function, we want to represent it with nth order Taylor polynomial plus the remainder. Ideally, the remainder goes to 0. If the remainder goes to 0, we can use nth order Taylor polynomial to represent the function. All right, so let's see. Yeah, of course, if it's we only go to 0 order of Taylor polynomial, so the remainder is everything, right? So the Rn has a formula, right? Basically, it's n plus 1 order derivative, evaluate at the center, divided by n plus 1 factorial, then multiply x minus a raised by n plus 1. Okay. This should have summation sign. So Rn. So basically, the rest of it, if we take a second order Taylor polynomial, so the remainder will be the third order. The remainder will be the rest of the terms, right? Okay, so Taylor's theorem with remainder. Let f be the function that can be differentiated n plus 1 times on an interval I containing the real number a. So let Pn be the nth order Taylor polynomial of f at a, and let the Rn representing the remainder be the nth remainder. Then for each x in the interval, there exists the real number c between a and x such that this. If there exists a real number m such that so it's bounded. Okay, this is not important for us. I'm going to skip this. All right, using linear and quadratic approximations to estimate function values. So this is important for us. So let's consider the function cubic root of x. Right? Think about the cubic root of 8. And the cubic root of 8 is a beautiful value, 2. Right? Cubic root of 27 is a 3. But what is the cubic root of 7? What's the cubic root of 6? What's the cubic root of 5? And we can punch into a calculator. When we punch into a calculator, the calculator does exactly Taylor polynomial or Maclaurin polynomial to approximate. So let's see this one. Find the first and second order Taylor polynomial for f at x equals 8. Well, that's easy, right? Because it's centered at 8. Use a graphing to compare. Okay. And B, use the two polynomials to estimate cubic root of 11. Then use Taylor's theorem to bound the error. So we need to find derivatives, right? So first order, we need to find the first derivative. Quadratic, okay. Linear means first order. Quadratic means second order. So we need to calculate the first order derivative. We need to calculate the second order derivative. Then we want to evaluate at the center 8. Because x equals 8 is the center. F of a equals 2. F prime of a equals 1 over 12. F double prime of a equals negative 1 over 144. Then we use the definition of Taylor polynomial. So P1 of x linear. Linear means first order equals to function value at a, which is 2, plus derivative of at a multiplied by x minus 8, which is 1 over 12 times x minus 8. Well, we see this is a linear function. So that's why it's called a linear approximation, all right? Because it's a linear function. What does this function do? This function can help us to find out cubic root of a.000001, right? Or cubic root of 7.999999 very, very close to 8, right? A number very, very close to 8. So we can use this linear approximation to approximate. So later on, we're going to approximate cubic root of 11. So second order means quadratic, right? So P1 part plus the quadratic term. So which is 1 over 144 multiplied by 2 factorial, multiplied by 1 over 2 factorial, which is 1 over 288 times x minus a squared. So we have a quadratic form, right? So P1 is a linear approximation for function cubic root of x. P2 is a quadratic approximation for cubic root of x, centered at 8. Centered at 8 means, when we want to center at 8, we want to approximate the values very, very close to 8, like 7.9, like 8.01, so on and so forth. So let's use this one to approximate cubic root of 11. Use linear, we get 2.25. Use quadratic, we get 2.21875. So we see 2.21875 is more accurate than 2.25. So for this bond, it's not so important for us. Okay, this is for math majored. Okay, so we need to know those two. We need to know. So given us a function, right, like a cubic root of x, we need to know how to use a linear linear Taylor polynomial to approximate or quadratic approximations. All right. So what do? We calculate the derivatives. We evaluate at the center. Right. Linear order, we get a linear function. A second order, we get a quadratic function. Then they just become a function, right? Then we can use this function to approximate a value very close to it. Well, the textbook use cubic root of 11. Usually we don't do that. Usually, we could do that, yeah. Usually we consider a value very, very close to 8, like 7.9, like 8.01. So this is exactly the calculators do, okay? A cheap calculator probably does a linear approximation. A very expensive calculator maybe do like a 1,000th order Taylor polynomial approximation. Okay, let's try one. Let's try this one. Let's try square root of x, right? Then let's try to find a linear approximation and a quadratic approximation, which means the first order Taylor polynomial or second order Taylor polynomial. Then we use them to approximate square root of 6. So we find the derivatives first. The center is 4. So I won't be able to talk about the next example, so we will talk about next time. So next week, it's our spring break. Okay, so let me see. So what I get is, so P1, I'm typing in the chat. P1 of x is a linear function, which is x minus 2. And the P2 of x is a quadratic function, which is x minus 2, which is x minus 2 minus 1 over 32 times x minus 4 squared. I plug in, I get a P1 of 6. I use this to approximate 6. I get a 6 minus 2, which is a 4. P2 of 6. After calculation, I get a 3.5, which is 7 over 2. Okay. So I hope you get the same. Anyone has any questions? Okay, if not, that's it. I hope you enjoy next, the spring break. Oh yes, right. Mathematics is like a piano, It's like a piano. When you know it, that's not enough. You have to practice. Okay, I see you after spring break. I hope everybody can take this time to rest. All right.